Hi everybody, Mr. Waiter here, and today we're going to be doing day 2 of our lesson on heat. So as a quick reminder, this is important for today. Energy tends to disperse, and it's going to do this from where you have more energy to where you have less of it. Meaning, for us, from a place that is hotter to a place that is colder. So, let's assume you have 3 containers and they each have 100 milliliters of water at 20 degrees Celsius. That's pretty cold. And then you add water to those containers. Each of them has hotter water being added, so the temperature is going to go up. Naturally, you would expect that if there's more water that's warmer, or you have hotter water, it'll increase the temperature more. So out of the 3, you've got 2 that are 80 degrees Celsius and 2 that have 500 milliliters. So you would expect the one that has the most and the hottest water to change the most, which it does. Notice it goes from 20 degrees to 70 degrees, and that's because you had 5 times as much water and it was 60 degrees hotter. Okay, so the largest change is there. How about if you split it? Now it's 100 milliliters of cold and 100 milliliters of hot. You have 20 degrees and 80 degrees. You would expect the average then to be in the middle, which is exactly what you get. 20 and 80 combined to give you 50 in this case, because that's the average of the two numbers. If you take 80 and 20 and then divide it by 2, that's 100 divided by 2, that's 50. This works because temperature is the average amount of energy out of all the things in the container. So as soon as it balances out, that's the idea of thermal equilibrium we talked about last time, it's going to meet in the middle at that median temperature. And it's called a weighted average, meaning it's averaging out towards whichever one has more of it. So in this case, we've got 500 milliliters versus 100 milliliters, but this is only 50 degrees Celsius. That's a 30-degree difference, but there's 5 times as much of this. Well, there's the ratio 1 to 5, and it goes up half of the 50 here. Goes up 25. The point that I want to get across to you at this point is that it's going to tend towards whichever one there's more of it, meaning the one that has more mass is going to control the temperature more. So it's going to be closer to the temperature of the one there's more of. And that, again, is because this is an average. So, to make sure we understand the difference between heat and temperature then, they are very different concepts. Heat is talking about the transfer of energy from one place to another, and temperature is telling you about the average amount of energy in the particles in that sample. This is why you can have 2 things that have the same temperature that are different sizes, and this is why your rate of transfer can be the same even though you have very different amounts of a substance. Heat is telling you about how much energy is going from place A to place B, and temperature is telling you how much energy there is on average in that area, in that container. And then the type of energy that we're talking about transferring around is thermal energy, and if you wanted to measure the total thermal energy, you would need to know the temperature and the amount of stuff that you have in the container. Again, these are 2 different size containers, but they have the same temperature. But what you would get is very different amounts of thermal energy, because the bigger container would have much more energy because there's much more stuff with the same average amount of energy. So the thermal energy depends on both the mass and the temperature. And if the temperature is the same in 2 containers, more mass means more energy. So that means this container on the right would have much more energy than the one on the left over here. Okay, the reason that I wanted to go through that first is because in order to understand this lava versus ice scenario, we need to understand how heat's moving around. So we've got lava, which is much hotter, being dropped on top of ice. And this is special ice. If you notice, it's very clear. There are almost no air bubbles. So it's not just going to crack and fall apart. It's going to only melt when the lava makes contact with the ice, and then it's not going to melt because of it cracking and separating. It's only because of the heat transfer. So, who do you think's going to win? Lava versus ice? Okay, so that's molten rock. Also, that sound effect, by the way, it's real. It's not post-production. When the air is trying to escape underneath the lava, it has nowhere to go. So it makes that whooshing noise as it shoots out from underneath the lava. So, the first time that I watched this, I couldn't really believe what the results were. And then, if you look at the math behind it, it makes sense, but, you know, it's kind of hard to believe at first that you have molten rock. Like, you melted a rock. That's not an easy thing to do. And this block of ice just stopped it cold. Like, really easily. By the way, if you ever played Minecraft, this is how you make obsidian. So, if we skip ahead a little bit here, you can see the final damage. And it's shocking how little actually gets done if you look at the block of ice. Look at that. It's like no damage done to it. It's possibly confusing. So anyways, what property of the ice makes it so good at preventing melting? Why is it so hard to turn that ice into water? Well, a couple things. First, we have specific heat capacity. Another idea we're not going to talk about in much detail is heat of vaporization or heat of fusion. And basically that's the amount of energy you need to take the ice and melt it. We're going to be focusing on specific heat capacity. And this is going to be a unique value for all different materials. And this is because each different substance responds to the transfer differently. And each different material takes a different amount of energy to change its temperature. You may have noticed some things are really hard to heat up. Like if you try to boil water, it takes a lot more work to do that than it does to, say, melt a stick of butter. That has to do with the fact that some materials naturally take more energy to change temperature. So, for example, water has a higher specific heat capacity than metals. That means metals take less energy to heat up a degree. So if you have a thermometer, you would want that thermometer to change temperature really quickly and really easily, right? So you can get a very specific number in a short amount of time, because nobody wants to keep a thermometer in their ear, mouth, or wherever for a really long time. And this is why the inside of thermometers are using metals that have things like copper, or silver isn't in the list, but silver is a good one too. Also explains why things that you're cooking with, you want to make sure have a slightly higher capacity. So you'd be using things like steel as opposed to, copper. Copper, if you look at pans, like the non-stick pans, the bottom of the pan will often have copper because it will take very little energy to heat that part up. But then once you get to the plate part of it, you usually have something like steel that's coated with a non-stick. And that's because you want it to be harder to heat up that part so that it heats up evenly inside the pan. There's your cooking lesson for the day. But anyways, this all happens because of specific heat capacity. Like I said, it's constant for each material. So, using this information, we could calculate exactly how much heat is transferred from place to place, or you could calculate how much of something you would need, or you can even calculate the specific heat capacity. Or you can make a prediction in the change in temperature if you know the other factors. The formula is Q equals MC delta T, or as I used to call it, Q equals MCAT, because that looks like an A. So Q is the heat, M is mass, C is the heat capacity, and delta T means change in T, which is temperature. So here's an example. If you have 50 grams of hot water at 70 degrees Celsius, and you pour that onto 59 grams of brass at 20 degrees Celsius, and the final temperature is 65.2, try to prove that the energy is conserved. Okay, a couple things here. First, there's two different things here. If we're showing the energy is conserved, this means we're trying to show that the amount of heat gained by one thing is the amount of heat that was lost by something else. So for that to happen, first, one thing should go up in temperature and the other should go down. If you take a look, the water is at 70 and then it drops to 65.2. And then if you have the brass, which is at 20 degrees Celsius, it goes up to 65.2. Okay, let's see if we can prove that those are the same. So mathematically then, we are trying to show that the energy is conserved and energy is being transferred as heat. Heat is the transfer of thermal energy. So we're looking over here, and the masses are given to us, and so is the change in temperature. Okay. So if we were to look this up in the chart we had there before, it's right over here. We have our metal, which in this case is our brass, and we have water. Water is 1 for specific heat capacity, and brass is 0.09. If we put these all together, what you'll see is that it is exactly the same on both sides here. So the mass is 50, drop that in for M, specific heat capacity is 1, and its change in temperature, it went from 70 down to 65.2. That's negative 4.8. So you get negative 240 calories. Okay, why is this number negative? Think about it. If its temperature is going down, it is giving away energy. So that's a negative amount because it's a change in a negative way. It is decreasing, therefore it's negative. The brass is absorbing the energy, so it should be positive because its temperature is going up. So 59 grams times its specific heat capacity for brass times the change in temperature, which is a very massive change. It went from 20 to 65.2. Much larger change than with the water. 240 calories. Notice that there is a much larger change in temperature for the brass, and that is because its specific heat capacity is much lower. So it takes much less energy to heat it up more. Okay, so that's cool and all, but why do we actually care about this? Like, melting things is neat, but how could this possibly matter for us as humans?
In this animation, we're taking Arctic sea ice into the third dimension. Here, we're looking at the ice age, which is an indicator of thickness. Generally, older ice is thicker ice.
That's the voice of Dr. Walt Meyer, senior research scientist at the National Snow and Ice Data Center.
What you see in this animation is the ice pulsing out and in with the seasons. In winter, the ice grows out and expands outward. In summer, it contracts inward as it melts. You see the whiter ice, which is the older ice, moving around the Arctic, being pushed around by winds and currents that move the ice. Over the years, the ice pulses around and moves around towards the top along the coast of Greenland. The older ice eventually moves out of the Arctic and into the North Atlantic, where it melts. The ice gets replenished within the Arctic because some of the ice survives each summer and grows older, and particularly in a region north of Alaska called the Beaufort Sea, where the ice spins around in a clockwise direction called the Beaufort Gyre. And that ice can keep spinning around oftentimes for several years.
But you may have been noticing that this ice is spinning around basically, and it's slowly coming from over here and going around over the top of Greenland.
Eventually, the ice will spin out of that gyre, and Graham Strait has not been compensated,
And what you'll notice,
allow the young
the
ice
farther
to
we
aid
go,
the older ice to, from a nursery
is we have
to
less and
older than
less
5 years
ice
old,
at
and
the
the
top
bright
there,
white is almost
and more of it
virtually
flowing
disappeared
away.
from the Arctic Ocean.
And that's problematic for a number of reasons. But just look at that difference. Same time of year, many years apart. But look at the difference. That's a lot of ice loss. So this concept of specific heat capacity may not be the thing that you're most excited about, but this is a really important phenomenon for us to understand. And it's explainable using this idea of specific heat capacity. So for your assignment today, what I'm going to ask you to do is to try and construct like a mental model of this and then turn that into a physical model. So to draw this on a piece of paper for me and then put some captions with a brief explanation of what's going on here. So this right here is the graph for the change in temperature over time as ice changes phase, meaning ice starts to melt. Now you have water and ice. Temperature goes up as it's melted, and now you're heating up the water. Now you need to take your water and turn it into steam. And then once you turn all of it into steam, then the temperature goes up. This directly relates to climate change. So do your best and try and turn this into a model for that. Meaning, where do you think climate change stuff that I just showed you in that video is happening here? And as a hint, this right here is ice and water. The ice would be the glaciers. So you're starting with the ice cap over where it says ice. And then just draw this graph. And I'll supply you with a picture of the graph. But try and make a rough sketch of this, and above it, write what you think is happening. As you go from ice all the way over to water vapor on the right, what are the steps that are happening at those polar ice caps based on this here? And then above those sections, write what's happening. So, for example, above ice, you would write glaciers. And then hopefully something related to those glaciers is what you would write above water and ice, etc.